Have you ever paused to think about what's really happening when your smartphone, instantly unlocks just by recognizing your face? Or how that streaming service seems to read your mind, suggesting the next perfect show before you even know you want it? Maybe you've even heard the incredible whispers about self-driving cars, navigating complex cityscapes with, well, uncanny precision. It can feel a bit like magic sometimes, can't it? As if there's some invisible, kind of intuitive intelligence at play, operating beyond our understanding. But the truth is far more fascinating, and I promise you, profoundly logical. It's not magic. It's built on the elegant and incredibly powerful language of mathematics.
Indeed. Beneath every one of these seemingly intelligent feats, machine learning truly speaks the language of mathematics. Today, our Deep Insight dialogue is dedicated to demystifying that language. We're going to embark on a journey through the fundamental mathematical concepts that transform raw, often messy data into truly intelligent actions. Our goal isn't just to define terms, but to explain everything as if you're encountering it for the very first time, making sure you grasp not just what these concepts are, but crucially, why they matter and how they empower machines to learn.
Absolutely. Our mission of this Deep Insight dialogue is to take a look at a fantastic resource, Mathematics for Machine Learning, and carefully pull out the most important, the most surprising, and the truly insightful nuggets of knowledge. This isn't just for, a general audience. It's specifically for you to give you a shortcut to being really well informed about the mathematical bedrock of AI. We're going to build your understanding from the ground up, one clear idea, one aha moment at a time. So what's on our agenda for today's exploration?
Well, we'll begin by dissecting the core components of any machine learning system: the data it consumes, the models it constructs, and the intricate process of learning itself.
Okay, data, models, learning. Got it.
From there, we'll journey through the four foundational mathematical pillars that support this entire edifice. That's linear algebra, analytic geometry, probability theory, and vector calculus, which includes the critical field of optimization.
The four pillars, right?
And finally, and this is where it all truly comes alive, we'll witness these powerful mathematical pillars in action. We'll explore how they seamlessly combine to tackle real-world machine learning problems.
The application part.
Exactly. We'll delve into everything from predicting continuous numbers to simplifying overwhelmingly complex data sets, uncovering hidden groups within our information, and even drawing remarkably precise decision boundaries.
It's going to be a truly illuminating exploration. Okay, let's unpack this. Before we dive into the intricate dance of the math, let's zoom out a little and establish our bearings. When we talk about machine learning, what are the absolute non-negotiable essentials we need for any system to even begin to function? What are the basic building blocks that are universally present no matter how sophisticated or complex the AI becomes?
Okay, think of it quite literally like building a house, a structure designed to perform a specific function. You wouldn't just show up with a hammer and nails and start building. Right. First, you need your raw materials, the wood, the bricks, the wires. Second, you need a detailed blueprint, a plan that dictates the structure and how everything fits together.
Like the plan.
And third, you need the actual construction process, the skilled labor that turns materials and blueprints into a finished home. In machine learning, these three essential components are your data, your model, and the learning process. Each one is not only critical on its own, but also deeply interdependent, constantly interacting and shaping the others.
That analogy of building a house really grounds it. So let's start with the foundational material, data. We're absolutely swimming in data these days, hearing that word constantly. But what is data in the specific context of machine learning? And perhaps more importantly, how do we represent it in a way that a computer, which fundamentally only understands numbers, can even begin to comprehend or process it?
Fundamentally, for machine learning to work, we must assume that any piece of information, no matter its original form, text, images, sounds, sensor readings, can be, well, converted into a numerical format. Imagine a massive table, much like a spreadsheet you might use every day. In this metaphorical spreadsheet, each row represents a single example or instance, maybe a person, a specific product, an email, or even a particular moment in time.
Okay, like one observation.
Exactly. And each column then is a feature or attribute that describes that example. So for a person, features could be their age, their annual salary, their geographic coordinates, or whether they prefer coffee or tea. Each of these becomes a number.
So if we're talking about a specific person, all their attributes, their age, their salary, where they live, would be lined up horizontally in one row. And together, that full row of numerical information would represent them as a single unique example in our system. That makes perfect sense for organizing information.
Precisely. And for a computer, this row, this collection of numbers that describes one specific example, becomes what we call a vector. It's the computer's incredibly efficient way of bundling all those individual pieces of information about a single entity into one coherent, mathematically manipulable unit. This abstract idea of a vector is truly a cornerstone.
This is where it gets incredibly powerful. For many of us, the word vector might conjure up images of a simple arrow on a graph, or maybe a term from a high school physics class. But a vector in machine learning isn't just a list of numbers, is it? It's a far more versatile concept, one that allows us to connect seemingly disparate ideas under a single mathematical umbrella.
It's an excellent point to emphasize. The true genius and perhaps surprising insight of vectors is their multifaceted nature. Even if you've never encountered vectors in a formal technical context, you can intuitively understand them in a few powerful ways. First, there's the most direct practical interpretation, the computer science view. A vector is simply an ordered array of numbers. For instance, if you're describing a person with their age, salary in thousands, latitude and longitude, that could be represented as, say, 36, 89.563, 51.5073, 0.1290. This is the most common, everyday, list-like representation.
Just a list.
Second, we have the physics view. A vector as an arrow with a direction and a magnitude. Imagine following directions on a map go 506 kilometers northwest. This view helps us visualize relationships and movements within our data, giving a sense of direction and scale.
Ah, like direction and distance.
Exactly. And finally, the more abstract yet fundamental mathematical view. A vector is an object that obeys specific rules, particularly addition and scaling. This view defines what you can do with a vector, regardless of what it conceptually represents. It provides a universal framework for manipulation. And what's truly remarkable here is that this single concept allows us to mathematically unify incredibly diverse real-world information.
Like what?
Well, think about an employee's salary data versus the intricate numerical patterns of an audio signal. A song, for example, is just a series of numbers representing sound waves. These numbers can be added together or scaled in volume, so mathematically it behaves just like a vector.
Wow, okay, so the math doesn't care if it's salary or sound.
Exactly. It means the same powerful mathematical tools can be universally applied. That's a cornerstone of AI's versatility.
That's a profound abstraction. So whether we're inputting detailed HR data about an employee, or processing a snippet of a podcast, or even analyzing pixels in an image, the computer ultimately transforms and treats it all as these amazing vectors. This common mathematical language is what makes machine learning so incredibly adaptable across vastly different domains.
Precisely. Once we have our data neatly transformed into these potent mathematical packets, our vectors, the next crucial step is to provide the machine with a framework for understanding and processing that data. This is where the model enters the picture.
So after our data is perfectly packaged as vectors, we need a model. This sounds like the conceptual brain, or maybe the analytical engine of the operation. What exactly is a model in this context, and what's its purpose?
A model is essentially a simplified, often mathematical representation of a real unknown process that generated your data. Think of it as a meticulously crafted blueprint that tries to capture the important aspects, the hidden patterns, and the underlying relationships within that data.
Like a blueprint for the data's origins.
Sort of. To extend our earlier analogy, imagine you're trying to understand how a really complex, intricate machine works, but you can't fully inspect all its internal gears and circuits. Instead of endless, costly physical experiments, you might build a simplified diagram, maybe a mathematical equation, or even a small-scale replica that captures its essential behavior. That diagram, that equation, that replica, that's your model.
Okay, a simplified representation, and why is that useful?
Well, zooming out, a good model's ultimate purpose is not just to describe how data is generated, but crucially, to predict what would happen in the real world without having to perform actual experiments. It allows us to simulate, to anticipate, and to make informed decisions based on patterns we've identified.
So we have the raw materials, our data represented as vectors. We have a conceptual blueprint, our model, which offers a framework for understanding and making sense of that data. Now, the million-dollar question: how does the machine actually learn from that data using this model? What's the dynamic process that brings the model to life?
Learning. This involves a continuous process of adjusting the model's internal settings, which we refer to as its parameters, based on the data we provided. We typically employ sophisticated numerical methods to make these adjustments iteratively, constantly tweaking and refining the model.
Tweaking the blueprint based on the materials.
Exactly. The overarching objective here is to minimize the discrepancy, the error, between the model's predictions and the actual observed data. The ultimate goal, and this is a critical distinction that separates true learning from mere memorization, is that our model must perform exceptionally well, not just on the data it saw during its training phase.
The data it's studied from.
Right. But
Uh,
more importantly, on new, previously unseen data.
That distinction, performing well on new data, not just rehashing or memorizing the old stuff, seems absolutely crucial. It's the difference between a student who truly understands a concept and one who simply crammed facts. But this raises an important question. What are the specific mathematical tools, the algorithms and techniques, that allow a machine to perform these precise adjustments and achieve this kind of deep understanding and generalization?
To answer that, we turn to the fundamental language that underpins all of machine learning mathematics. It's not just one branch of mathematics, but rather a powerful interconnected combination of several pillars, each contributing its unique strengths to the learning process.
Now that we know data gets neatly organized into vectors and models act as our conceptual blueprints, how do we actually manipulate and work with these data structures, especially when we're dealing with vast quantities of information? How do we organize them, transform them, and compare them effectively? This is where our first pillar, linear algebra, steps in, giving us the foundational tools to handle these structural aspects of data.
You've hit on a crucial point. If a vector is a list of numbers representing a single example, then a matrix is essentially a table of numbers, or you can think of it as a collection of many vectors stacked together. They are absolutely central to linear algebra because they provide an incredibly compact and powerful way to organize and manipulate entire data sets or even complex systems of relationships all at once.
Like that HR data table you mentioned earlier, the whole spreadsheet is a matrix.
Exactly. That entire table is a matrix. Each row is a vector representing a person, and the whole table is the matrix holding all those people.
So matrices are like super spreadsheets for computers, capable of holding vast amounts of data in a highly structured way. But beyond just holding data, what kind of powerful operations can we perform on these matrices? How do we use them to process and transform information?
While some operations are quite intuitive, matrix addition, for instance, is straightforward. You simply add corresponding elements, much like merging two compatible spreadsheets cell by cell. Simple, but vital for combining data.
Okay, adding them up makes sense.
But matrix multiplication is where the magic truly unfolds, and it's often a conceptual leap for newcomers. What's truly fascinating here is that it's not element by element like you might intuitively expect. Instead, it's a more complex dot product operation performed between the rows of the first matrix and the columns of the second.
Rows times columns. That sounds...
different.
Why so complicated?
This complexity is not a bug, it's a feature. Matrix multiplication isn't just about combining numbers. It often represents applying a transformation or mapping one set of numbers to another. Think of it like a recipe scaling ingredients. You don't just multiply everything by the same amount, but specific combinations are made to achieve a new result.
A transformation, like rotating or stretching something.
Precisely. And a profound insight here is that if you multiply matrix A by matrix B, the result AB is often not the same as BA. The order in which you apply transformations absolutely matters.
Ah, like putting on socks then shoes is different from shoes then socks.
Exactly. A perfect analogy. This isn't just a mathematical quirk, it's a deep insight into how sequences of operations combine. The order dictates the outcome, mirroring how, in the real world, doing things in a different sequence leads to vastly different results. This makes matrix multiplication indispensable for modeling dynamic systems and layered operations in machine learning.
That's a truly illuminating distinction, that matrix multiplication is about transformation and the order matters.
Mm-hmm.
Okay, so matrices give us these powerful tools for compactly representing and transforming complex systems. But once we've organized and potentially transformed our data, how do we then understand the relationships within that data? How do we measure if two vectors or data points are similar or different in a meaningful way?
To measure how alike vectors are or how far apart they are in our conceptual data space, we need geometry. This is where analytic geometry introduces two critical concepts: norms for measuring distances and inner products for measuring similarity or the angle between vectors.
Norms and inner products. Okay.
The most common norm, the Euclidean norm or L2 norm, is precisely what you intuitively think of as distance, the straight line distance. Just like you'd calculate between 2 points on a map, it tells us the length or magnitude of a vector or the distance separating two data points.
Like using a ruler in this data space.
Exactly. Inner products, on the other hand, allow us to introduce concepts like the angle between two vectors. If the inner product between two vectors is 0, the vectors are orthogonal, meaning they are completely unrelated or geometrically perpendicular to each other.
Orthogonal,
Mm.
perpendicular.
Yes. And this is an incredibly important concept in machine learning because it helps us identify independent features in data.
Orthogonal, so like two perfectly perpendicular lines or dimensions. How does that abstract idea of perpendicularity help us with data that might have many, many dimensions, far beyond what we can visualize?
That's a perceptive question, and the answer is surprisingly elegant. Yes, if two features in your data are orthogonal, it means that knowing the value of one feature tells you absolutely nothing about the value of the other. They are independent dimensions of information.
Ah, so they don't overlap in the information they carry.
Precisely.
Ah.
This is incredibly useful for simplifying data, for instance, by identifying and removing redundant features and for finding its true core essence. This understanding naturally leads us to a fascinating question. If we want to simplify our data and distill its most crucial elements, how do we find these essential non-redundant pieces of information that truly explain its structure? To get to the essence of information in our data, we introduce the concepts of basis and rank. We can often describe any complex vector using a simpler, minimal set of fundamental vectors called a basis. Think of it like having a minimal set of fundamental directions that can get you anywhere in a city.
Like north, south, east, west.
Kind of. For example, if you want to give directions to Kigali, Rwanda, from Nairobi, Kenya, you might say, go 506 kilometers northwest to Kampala and then 374 kilometers southwest to Kigali. Those two directions, northwest and southwest, are linearly independent and form a basis because they're sufficient. If you then added, it's about 751 kilometers west of here, that third statement, though geographically true, isn't necessary. West can be described as a combination of northwest and southwest. It's redundant information in that context.
So a basis is like finding the most compact core set of non-redundant instructions or dimensions that can describe everything else. And then what does rank tell us about our data?
Exactly. Building on that, the rank of a matrix tells us the number of truly independent directions or features that genuinely contribute unique information to our data. It's about finding the essential, non-redundant information that defines the data's true dimensionality and complexity. If a matrix has a low rank, it means much of its information can actually be described by a smaller number of these fundamental directions, which is a powerful insight for data compression and understanding.
Matrices, with their ability to organize and transform data, can still seem like big, opaque blocks of numbers, almost like a black box. Can we actually break them down into simpler, more fundamental components to truly see how they work, to understand their inner mechanics and what they're doing to our data?
Absolutely. That's where the truly insightful world of matrix decompositions comes in. They're like taking a complex machine apart to understand its individual gears and levers. Instead of one opaque matrix, we get several simpler ones that, when multiplied back together, reconstitute the original matrix.
Taking the matrix apart to see inside. Okay.
Two critical decompositions for machine learning are eigendecomposition and singular value decomposition, SVD. For square matrices, eigendecomposition reveals special vectors called eigenvectors and their corresponding eigenvalues. Imagine a transformation like stretching, squashing, or rotating a shape in space. Eigenvectors are the unique, special directions that do not change direction during this transformation. They just get scaled.
They point the same way, just get longer or shorter.
Exactly. The eigenvalue then tells you how much they're scaled, how much they're stretched or shrunk along that invariant direction.
So using that funhouse mirror analogy, your eigenvectors would be the parts of you that just get taller or shorter, perhaps wider or narrower, but without twisting or turning. That's a fantastic way to visualize it. And how is this abstract concept of eigenvectors used in the real world to build something practical?
Precisely. Your analogy is spot on. A classic, perhaps surprising, real-world application is Google's PageRank algorithm. It famously used eigenvectors to determine the importance of web pages by analyzing the intricate link structure of the entire internet. The eigenvector corresponding to the maximal eigenvalue indicated the most important pages, those receiving many links from other important pages.
Oh, so eigenvectors help rank websites.
Yes. If we connect this to the bigger picture, it strikingly demonstrates how abstract mathematical concepts like eigenvectors underpin some of our most common everyday digital experiences, dictating what you see first in a search result. It's truly a testament to the power of mathematical abstraction.
That's incredible. What about the other one, SVD?
Singular value decomposition, SVD. This is even more powerful, especially because it works for any matrix, not just square ones. SVD decomposes any matrix into three simpler matrices, revealing how it transforms data through a sequence of rotations and scaling in a highly structured and revealing way.
So it works on rectangular matrices too, like our HR data.
Exactly. Think of it like looking at a complex 3D object from different angles. SVD gives you the essential 2D shadows that best represent the object, along with how much each shadow contributes to the overall structure. It essentially finds the most important independent patterns in your data.
Finding the best shadows or views. How's that used?
This is used extensively, for example, in analyzing vast movie rating datasets to discover underlying themes or user preferences, like identifying a science fiction lover or someone who prefers romantic comedies based on how they rate movies. This insight is then crucial for building intelligent recommendation systems that understand what you might like next.
Wow. Okay, so we've covered how to structure our data with linear algebra, measure its relationships with geometry, and even break down complex transformations to understand their core effects with decompositions. But the real world, as we all know, isn't always neat, tidy, or perfectly predictable, like our mathematical examples. There's always an element of uncertainty, randomness, or things we simply can't perfectly predict. How does mathematics, our precise language, handle that crucial inherent fuzziness of the real world?
That's precisely the realm of our next pillar, probability theory. It provides us with a consistent, rigorously mathematical framework to reason about uncertain outcomes, to quantify our confidence in predictions, and to model the inherent variability and unpredictability we encounter. It moves beyond simple yes-no to how likely is it, allowing us to make informed decisions even in the face of incomplete information.
That sounds absolutely essential for any kind of intelligent system interacting with the real world. But where do we even begin to define possibilities and uncertainties in a structured way? It feels like a big conceptual leap from deterministic math.
The initial step is to precisely define all possible outcomes of an event, which we call our sample space. For example, if you're drawing two coins from a bag containing both US and UK coins, your sample space would include every combination, all the possibilities.
Listing everything that could happen.
Exactly. Then a random variable comes into play. This is essentially a function that assigns a numerical value to each of these outcomes, transforming qualitative events into quantitative measures. In our coin example, the random variable x could represent the number of US coins you drew. So x21, x11, x101, and x11, it is 2. This gives us a numerical, measurable way to consistently talk about uncertain events.
Turning outcomes into numbers.
Okay.
Is probability always about counting these discrete possibilities, like with those coins where we're counting how many US coins we get? Or can it apply to things that aren't so easily countable?
That's a crucial distinction. We categorize probabilities into discrete and continuous types. For phenomena, you can count like the number of heads in coin flips or the number of spam emails per day. We use probability mass functions, PMFs. These give you the exact probability for each specific countable outcome.
Like a bar chart showing the probability of 0, 1, or 2 US coins.
Exactly. However, for things you measure like a person's height, the temperature, or the precise time a machine fails, these are continuous outcomes. For these, we use probability density functions, PDFs. You can't assign a probability to a single exact height, like exactly 175.32145 centimeters. Instead, you talk about the probability of a value falling within a range, like between 175 centimeters and 176 centimeters.
So PMF is like bars. PDF is like a smooth curve.
A good way to visualize it, yes. The area under the PDF curve over an interval gives you the probability for that range. This distinction is critical in machine learning. Predicting discrete categories like spam or not spam often involves PMFs. But forecasting continuous values like stock prices uses PDFs. Understanding which one you're dealing with dictates the whole statistical framework.
That really clarifies how we quantify different types of uncertainty. So, with these sophisticated ways to define and measure possibilities, what are the fundamental rules or theorems that allow us to work with and manipulate probabilities? Are there golden rules that govern how we calculate and update our beliefs?
Absolutely. There are a few fundamental rules. The sum rule helps us calculate the total probability of an event, especially when there are multiple ways it can happen. The product rule helps us figure out the probability of two or more events happening together, their joint probability. But the superstar, especially in machine learning, is unequivocally Bayes' theorem.
Bayes' theorem. I've heard of that one. Why is it such a big deal?
This theorem is how we formally and rationally update our beliefs in the face of new evidence. It tells us how to calculate the probability of something, let's call it X, or hypothesis, given some new evidence, Y. It masterfully combines our initial belief about X, what we call the prior probability, with the likelihood of observing y if x were true, the likelihood, adjusted by the overall probability of y happening, the evidence.
So it's not just about updating your mind, it's about doing it formally and rationally based on new information. Can you give us an everyday, perhaps even counterintuitive example of how Bayes' theorem truly works its magic?
Certainly, think about a medical test for a rare disease. If you get a positive test result, your immediate thought might be, oh no, I definitely have the disease.
Hmm,
But Bayes' theorem reveals a deeper truth. It helps you calculate the actual probability of having the disease given that positive test. This often depends heavily on how common the disease is in the population, your prior belief, and how accurate the test is, the likelihood.
So even if the test is pretty accurate, if the disease is super rare, a positive result might still mean I probably don't have it.
Exactly. It's often counterintuitive. What's often surprising is how much our initial belief, our prior, can influence the final probability, even with strong evidence from the test. It teaches us to be humble about initial conclusions and constantly update our worldview with new, concrete information, a surprisingly human lesson embedded in pure mathematics.
Yeah.
It allows for incredibly powerful and rational decision-making under uncertainty.
that's fascinating. Okay, beyond these rules, how do we summarize probability?
Well, we often want to summarize a complex probability distribution with just a few key numbers. The mean, or average, tells us the central tendency where the values generally cluster. The variance tells us the spread or dispersion, how much the values typically deviate from that mean, giving us a measure of uncertainty. And the concept of independence is crucial. If two events are independent, knowing one tells you nothing about the other, which often simplifies calculations dramatically.
I mean, variance, independence, standard
Yeah.
statistical concepts. Got it. And when we talk about probability distributions, there's one that almost everyone has heard of, even if they don't know its name, the bell curve, or the Gaussian distribution.
Yeah.
Why is it so ubiquitous and special in probability and, by extension, in machine learning? Why do we see it everywhere?
The Gaussian or normal distribution is indeed incredibly important, almost miraculously so, because it arises naturally in such a vast array of phenomena. The central limit theorem, a truly profound result in statistics, explains why. The sum, or average, of many independent random variables, even if those individual variables aren't Gaussian themselves, tends to converge and look Gaussian.
So lots of random things added up start looking like a bell curve.
That's the essence of it. Think of measurement errors, natural variations in biology, noise, and sensors. They very often follow this iconic shape. Crucially for machine learning, it possesses incredibly convenient mathematical properties that make calculations much easier and often yield elegant, closed-form solutions. It's frequently used for modeling noise, as priors for model parameters, and as likelihoods for data in many models, significantly simplifying the underlying math.
So we have incredibly powerful ways to represent data, models to structure our understanding, and probability to elegantly handle the inherent uncertainty of the real world. But with all these pieces in place, how do we actually find the best model? How do we adjust its parameters, its internal settings, to minimize errors and make the most accurate predictions possible? This sounds like a complex navigation problem across a vast abstract landscape.
It absolutely is a navigation problem, and our next pillar, vector calculus, provides the indispensable map and compass for that very journey. The key concept here, the one that tells us precisely which way to go, is the gradient.
The gradient, okay, like the slope of a hill.
Exactly. For a simple function with just one input, a derivative tells you the slope, how much that function changes if you tweak its input just a little bit. For functions with many, many inputs, which is exactly what we have in machine learning models with their numerous parameters, the generalization of the derivative is the gradient. It's a vector that points in the direction of the steepest descent on our metaphorical error landscape.
So if I were blindfolded on a vast, undulating mountain range and wanted to get to the peak as fast as possible, the gradient would tell me precisely which way is straight up.
Precisely.
And conversely, if I wanted to go downhill, perhaps to minimize an error or loss in our machine learning context, I'd simply go in the opposite direction of that gradient.
Exactly. It's our indispensable guide for making incremental, informed improvements. However, machine learning models, especially deep neural networks, can be incredibly complex, built from many layers of calculations stacked upon each other, what we call composite functions. How do these gradients work their way through all that intricate complexity? How do we know how adjusting something at the start affects the final output way at the end? That's where the chain rule is not just vital, but truly ingenious. It's a fundamental rule for differentiating composite functions that are built from other functions, like nested mathematical operations. The chain rule tells you precisely how a change in an initial input propagates through a series of sequential steps to ultimately affect the final output.
Like a chain reaction.
A perfect way to think about it. Imagine a long, intricate assembly line where each station performs a different modification. The chain rule helps you figure out exactly how adjusting the first step affects the final product, even with many intermediate steps. In machine learning, this is the mathematical backbone of backpropagation, the groundbreaking algorithm used to efficiently train deep neural networks. This allows those incredibly complex AI models, with millions or even billions of parameters, to learn from errors and improve. Without the chain rule, training these models would be computationally impossible.
So the gradient gives us the direction of steepest descent or descent, and the chain rule provides the means to calculate that direction even in super complex layered models. But knowing the direction isn't enough. How do we actually use that information to systematically roll down the hill and converge on our optimal model parameters? What's a practical process?
That's where our final pillar, continuous optimization, steps in, providing the algorithms to systematically search for the best solution. The most fundamental and widely used algorithm for this process is gradient descent.
Gradient descent. Okay, the name makes sense now.
It simply takes small, iterative steps in the direction opposite to the gradient. We repeat this process, gradually moving down the error landscape, striving towards a local minimum of our error function or loss function, the point where the model's predictions are as accurate as possible.
So it really is quite literal. Rolling a ball down a hilly landscape until it settles in a valley. But I've often heard that sometimes, especially in certain types of landscapes, gradient descent can be agonizingly slow, almost like zigzagging back and forth without making much progress towards the bottom of the valley. Is that a common problem?
You're absolutely right to pick up on that. The source material has a great illustration, figure 7.3, of this zigzagging phenomenon, which happens in what we call poorly conditioned problems. When the error landscape has long, narrow, canyon-like valleys, the gradient can point nearly perpendicularly to the shortest path to the minimum. This forces the optimization to bounce back and forth inefficiently across the valley walls instead of smoothly following the floor down.
So it gets stuck bouncing side to side instead of going straight down the canyon.
Exactly. This is why, while basic gradient descent is foundational, we have developed smarter, more efficient versions to navigate these complex landscapes more effectively.
That makes perfect sense for those tricky valleys. But what if our data set and model is so enormous, with millions or even billions of data points, that calculating the exact downhill direction at every single step using all that data is just too slow, maybe even impossible?
That's a very common, indeed almost universal scenario in modern machine learning. The elegant solution here is stochastic gradient descent, SGD. Instead of using all the data to calculate the gradient at each step, which is called batch gradient descent, SGD uses only a small random subset of the data, what we call a mini-batch.
Stochastic meaning random, so it uses a random sample.
Precisely. It's like taking a noisy, approximate compass reading. While each step might be a bit less precise or a little wobbly, the sheer speed of each step means that over many iterations, it converges incredibly efficiently, especially for massive data sets.
Faster steps, even if they're a bit approximate, get you there quicker overall on huge data sets.
That's the idea. This allows us to train models on data sets that would be impossible to handle otherwise. SGD is, in fact, the dominant algorithm for training large-scale machine learning models like the deep neural networks, powering so much of today's AI.
So SGD gives us the vital speed we need for massive data sets. But what if we have to optimize our model, yet there are strict rules or boundaries that our solutions simply must adhere to? For instance, if you're trying to find the best possible diet, but you're strictly constrained to spend less than $100 a week and consume fewer than 2,000 calories, how does optimization handle those kinds of non-negotiable boundaries?
That's the complex yet critical challenge of constrained optimization. Here, we use powerful techniques like Lagrange multipliers to ingeniously incorporate these rules or boundaries directly into our optimization problem. Imagine trying to find the lowest point in a valley, but you're strictly constrained to stay on a specific winding path along the hillside.
You can't just go straight down, you have to follow the path.
Exactly. Lagrange multipliers elegantly combine your original objective, finding the lowest point, with your constraints, staying on the path, into a single, new, unconstrained function. This transformed function now has special points, saddle points, where the gradient is 0, which conveniently correspond to the constrained optimal points of your original problem. This makes it solvable with standard gradient-based methods.
A clever trick to turn a constrained problem into an unconstrained one.
It is very clever. And this is absolutely critical for many machine learning models, especially something like support vector machines, SVMs, in classification, where we want to maximize a margin of separation while simultaneously ensuring that all data points are on the correct side of a decision boundary. The constraints are just as important as the objective function itself.
Wow. Okay. From representing data as vectors and matrices to understanding uncertainty, navigating error landscapes with calculus, and finding the best solutions even with rules through optimization, we've truly built up an incredibly powerful mathematical toolkit. Now let's bring it all together and see how these math pillars combine to build actual machine learning models that solve tangible, real-world problems. First up, predicting continuous numerical values like house prices, stock fluctuations, or even tomorrow's temperature.
Here we turn to linear regression, one of the most foundational and widely understood machine learning models. It uses linear algebra to find the best fit line, or more generally, a hyperplane, which is just a fancy word for a flat surface in more than 3 dimensions, through a set of data points to predict a continuous numerical value.
Finding the best line through the data points.
Exactly. In action, linear algebra gives us the structure. Vectors represent individual data points, like house's size, number of bedrooms, location, and matrices neatly organize our entire data set of many houses. Then, optimization takes over, precisely minimizing a squared error losses function using gradients to find the optimal parameters, the slope and intercept of that best fit line.
Adjusting the line until the errors are smallest.
Right. And crucially, probability theory, often leveraging the Gaussian distribution, isn't just an afterthought. It helps us understand the inherent noise and uncertainty in our data and predictions. It lets us quantify the likelihood of our model's fit, building confidence in our predictions.
That elegantly ties several pillars together. But what if that best fit line seems to fit the training data perfectly? Maybe wiggling through every single noisy bump and outlier, but then completely misses the mark when presented with new, unseen data. That's what we call overfitting, right? And it sounds like a big problem for a model that's supposed to generalize.
Precisely. Overfitting is indeed a very common and critical problem. It occurs when a model essentially memorizes the training data, including its noise, instead of truly learning the underlying generalizable patterns. It's like that student who memorizes answers but can't apply concepts.
So how do we stop the model from just memorizing?
The solutions involve powerful techniques rooted in our mathematical pillars. Regularization, which emerges from optimization, or Bayesian linear regression, which leverages probability. Regularization works by adding a penalty to the model's complexity during optimization. It discourages the model from becoming too flexible or wobbly. This penalty effectively encourages simpler, smoother solutions less prone to memorizing noise.
Penalizing complexity to keep it simple.
Right, like L1 or L2 regularization. Bayesian linear regression, on the other hand, takes a fundamentally probabilistic approach. Instead of finding a single best line, it considers an entire distribution of plausible lines, averaging their predictions. This inherent uncertainty quantification helps it generalize better and provides a more robust prediction.
Okay, that covers predicting numbers and managing overfitting. But let's imagine we have incredibly complex data, maybe something like images of handwritten digits. Each image might have thousands of pixels, meaning thousands of individual features or dimensions. How do we begin to make sense of that without getting completely overwhelmed?
This is where dimensionality reduction, and specifically principal component analysis, PCA, becomes absolutely indispensable. PCA is a powerful technique rooted in linear algebra and analytic geometry designed to simplify complex, high-dimensional data. It finds the most important directions or principal components within that data, allowing us to represent it in a much lower dimension, often with surprisingly minimal loss of crucial information.
So it's almost like taking that squashed, slinky analogy we discussed earlier. Even though it's 3D, its essential coiled structure can be mostly captured by describing its path along a simple 1D line. PCA performs that amazing feat for your data.
That's a perfect analogy, truly capturing the essence. The mathematics in action here is quite profound. PCA first computes the covariance matrix of the data. This matrix summarizes how variables change together, revealing the underlying shape and spread of our data.
where the data varies the most.
Exactly. PCA then identifies these principal directions by finding the eigenvectors associated with the largest eigenvalues of this covariance matrix. Remember those from linear algebra. These eigenvectors literally point along the directions where the data varies the most.
Using eigenvectors to find the main directions of variation. Cool.
Right. Once these optimal directions are found, PCA then projects the data onto these chosen lower dimensional principal components using analytic geometry. The purpose: simplify data for visualization, like turning thousands of pixels into 2D points on a graph, reduce computational cost, and remove noise, all while retaining as much variance the spread of information as possible.
That's brilliant for simplifying complexity. But what if our data doesn't follow a simple single bell curve? What if instead it looks like there are multiple distinct groups or clusters within our data, but we don't know what those groups are beforehand? How do we mathematically uncover those hidden structures?
That's a perfect scenario for density estimation, and specifically Gaussian mixture models, GMMs. GMMs provide an incredibly flexible way to model complex data distributions that appear to have multiple bumps or clusters. They do this by cleverly combining several simpler Gaussian distributions, each assumed to represent a different underlying cluster.
Like finding multiple bell curves hidden in the data.
Exactly. Imagine you're looking at heights in a school assembly with both elementary kids and high school seniors. A single bell curve won't fit well, but 2 or 3 bell curves, each centered on an age group, would capture the overall distribution much better. GMMs mathematically discover those individual bell curves.
That makes a lot of intuitive sense. So it's about finding the underlying, often hidden, patterns and groupings. How do GMMs actually employ the mathematical pillars?
GMMs rely heavily on probability theory and, as the name suggests, the Gaussian distribution. Each component is a Gaussian with its own mean and variance. However, finding the optimal parameters for a GMM, the mean, variance, and proportion of each Gaussian component is complex because the components are intertwined. We don't know which data point belongs to which cluster initially.
It's a chicken and egg problem.
Sort of. This is where iterative optimization comes in, specifically an elegant algorithm called the expectation maximization, EM algorithm. It's a clever two-step cycle. In the expectation step, it guesses which cluster each data point most likely belongs to, based on current parameters. Then, in the maximization step, it refines the cluster parameters based on those guessed assignments. It repeats this, iterating and refining, until it stabilizes.
Guess, refine, until it fits.
Exactly. The purpose is incredibly useful: identify underlying groups, understand complex data shapes, and even generate new data resembling the original distribution.
Finally, let's turn our attention to one of the most common and practical machine learning tasks: sorting things into categories. Think spam or not spam, or different types of images. How do we get machines to draw those incredibly smart, precise decision lines or boundaries?
For classification, one of the most elegant and powerful models is support vector machines, SVMs. SVMs are powerful classifiers that primarily use a beautiful blend of analytic geometry and constrained optimization to find the best dividing line or hyperplane between different categories of data.
Finding the best separator.
But the core idea is truly insightful. SVMs don't just find any line that separates the data, they search for the line that creates the widest possible buffer zone or margin between the closest data points of different categories.
So it's not just about separation, it's about achieving the most confident and robust separation possible. Like if I had blue and orange marbles on a table, an SVM wouldn't just draw a line, it would find the widest possible ruler I could place between them, maximizing that comfort zone.
Exactly that. Your analogy perfectly captures the essence, like figure 12.4 in the source. The wider that margin, the more robust the classification will be for new data. Mathematically, SVMs heavily use analytic geometry to define these hyperplanes and calculate distances, identifying those support vectors, the points closest to the margin. Crucially, they employ constrained optimization with Lagrange multipliers to maximize this margin while ensuring all data points are correctly classified. It's a beautifully constructed optimization problem.
But what if our data isn't neatly separable by a straight line? What if our blue and orange marbles are all mixed up? Or maybe the orange ones form a circle around the blue ones? A linear separator seems impossible there.
That's a classic challenge: non-linearly separable data. The brilliant solution is through a mathematical trick called kernels. Kernels are incredibly clever. They allow SVMs to implicitly transform your data into a higher, more complex dimension where it can be linearly separated without ever actually performing the computationally expensive explicit transformation.
Whoa, so it pretends to move the data to a higher dimension where it is separable.
Essentially, yes. Imagine trying to separate red dots inside a ring of blue dots on a flat plane, impossible with a line. But if you could conceptually lift the red dots into a third dimension, maybe based on distance from the center, suddenly a flat plane could easily separate them. Kernels do this lifting mathematically, allowing us to find complex, curved decision boundaries in the original space by doing linear separation in a cleverly chosen higher dimensional space. It's an incredibly powerful concept. Hashtag outro.
Wow, okay. From transforming raw data into vectors and matrices to handling uncertainty, navigating error landscapes, and drawing smart boundaries, we've truly covered a fascinating and intricate mathematical landscape today in this Deep Insight dialogue.
Indeed. This dialogue has hopefully shown that these mathematical concepts are far from abstract ideas confined to dusty textbooks. They are the fundamental living language that allows machines to learn, to understand, and to intelligently interact with our incredibly complex world.
So what does this all mean for you? It means that the seemingly magical intelligence you encounter every day, from recommendation engines to facial recognition, is built on an incredibly powerful foundation of elegant, logical mathematics. Understanding these fundamental pillars empowers you to not just passively use AI, but to truly understand how it works, and perhaps even to critically question why it makes certain decisions. It pulls back the curtain a bit.
This knowledge is an invaluable tool, not just for those who build AI, but for everyone who engages with it. It equips you to differentiate between genuine innovation and mere hype, and to discern the underlying principles at play.
So, as machine learning continues to evolve at breakneck speed, what new mathematical insights do you think will drive the next generation of AI breakthroughs? And how can your newfound understanding today help you interpret and critically engage with the intelligent systems that are already shaping your world right now? Thank you for joining us on this deep dive into the mathematics of machine learning. We hope you feel a little more well-informed and perhaps a lot more curious.
Keep exploring, keep questioning. There's always more to learn in this fascinating domain.